All right, so before we start talking about anything, I want you guys to do something. So some of you, I didn't have enough for everybody, but because I don't have enough of these for everybody, but some of you have a copy of this activity and 2 molecular models. So with whoever you can around you, if you don't have models or activity, lean over the shoulders of somebody who does and get to work. You have 4 or 5 minutes to answer the questions on this piece of paper. You can write them down, you can talk about them. Use these models to try to figure it out. I will walk around, and I'll be outside too, answering any questions that you have. So I'll see you in about 4 or 5 minutes. Get to work. Okay, can I have everyone's attention? Can I have everyone's attention, please? Excuse me. Please stop working on organic chemistry. Okay. All right. So, thank you. It's very nice to be here. Thank you to our organizers. Thank you for, I really appreciate having the opportunity to talk about something I'm really super excited about. Obviously, you guys were pretty excited too. It's hard to bring you back. What you guys were just experiencing is a teaching method called process-oriented guided inquiry learning, and you were working to discover one of the key concepts in organic chemistry, which is that an object, such as one of the models you have in your hand, and its mirror image are sometimes not superimposable. They're not the same. Your right hand is different from your left hand. In the same way as the 2 models you were supposed to have built would not be the same as each other. This is a very important concept in biochemistry and in drug design and lots of other fields. And the students would work for about 45 minutes on this activity with some extra questions, and they would all discover this very important concept for themselves. So the POGO project is funded by the National Science Foundation and the U.S. Department of Education. And from Stanford, that's just where I did my PhD. I'm living in San Miguel, working on this type of learning. So this learning method was developed. It's cut off. Oh, no. So this teaching method was developed because there's a crisis of passion and creativity in science. And this is largely because of the way we teach science. The way we teach science is primarily with lecture. And lecture reinforces negative views of science, in particular that science is this uncreative tabulation of immutable facts handed down from somewhere on high to be memorized by students. Okay, that's students' impression of what science is, and lecture completely reinforces that. And as a result, they resort to what I call academic bulimia, which means right before the test, they try to gobble up all these bits of facts and information, and then right after the test, they invariably, because of the way the mind works, they forget it, and it's of no use to them, almost no use to them, is including physicians in medical school. So that should scare you a little bit. The other thing is that memorization is very boring. And as a result, students conclude that science is boring. All right? And that might seem like not very important maybe, but it turns out it's not working? I'm back? Okay, a lot of people sit in their science classrooms their freshman year and say, to hell with this. I'm not going to sit here and listen to this dreary facts. I'm going to do something more interesting, art, writing, poetry. Well, the world would be a much, much better place. I know a lot of chemists. The world would be a much better place if more poets and artists knew a lot of organic chemistry. There would be much better policy decisions made, much more interesting chemistry taking place. So the result is lack of diversity of thought in science. So there are currently, there are really no widely accepted alternatives to lecture. The interest in this method, POGL, and other similar methods has been growing very rapidly in the last few years, and I'm going to tell you something about that. So first, let me start with research on how people learn, because that's how we started trying to develop this teaching method. These are two great books, How People Learn and The Art of Changing the Brain. There are hundreds of books on how people learn. There are thousands of articles, many, many years of research. If we had to boil all that research down into 3 bullets, they would be, 1, that teaching by telling does not work. Okay, I'm wasting my breath right now, probably. Students learn more when they have an opportunity to construct their own understanding, something called constructivism. And lastly, that discussion with peers is crucial. Learning is a social act, and you really need to work with your peers, not necessarily with people, experts, but with your peers. Okay, so what is this POGL learning method? So we don't have sound on this. Is there a way to get sound on that? All right. If you had sound on this video, you'd hear a rush of talking and people moving around, some of these people moving around our TAs. Students working in groups of 3 or 4. Oh, thank you. All right, so students are working in groups of 3 or 4. The instructor is acting as a facilitator, just as I was trying to do very briefly at the beginning of this talk. And students are working on these specially designed guided inquiry activities, not unlike the ones that you were working on. Over 30,000 students at hundreds of institutions are currently using this mode of instruction in their classroom as their primary mode of instruction. Mostly in chemistry and biology, because the people who started POGL were chemists and biologists, and we wrote materials for chemistry and biology. We're moving out now into mathematics. I'm here in San Miguel actually writing activities in collaboration with calculus professors in the States for calculus, pre-calculus, and other really important topics that probably many of you tried to take in college and said, like many other creative people, I'm not going to sit here and memorize all this stuff. Okay, what's the point? What's the point? Okay, so recently, a lot of attention has been devoted to this in Science, which is the premier academic periodical in the United States. Did a couple of articles last year on this type of learning. At MIT, they've gotten rid of lectures in their physics department. Last year, the POGL project won, or was a finalist, a runner-up in the 2009 WISE Award competition sponsored by the Cutter Foundation. 2 of our high school teachers went to the White House and accepted from President Obama the Presidential Award for Excellence in Science and Math Teaching. And last month in CNE News, which is the largest read trade periodical in chemistry, 140,000 people read that every week. The cover story last month was Pedagogies That Work, and it featured the POGL project in that article. So why does POGL work? POGL works because it reveals science as a creative process. What you guys were doing was trying to construct your own understanding of these models. Maybe you didn't make much headway, you didn't have a lot of support, and you don't have a lot of background. This is hard stuff. But it reveals science as a creative process. Instead of memorizing stuff, you are actively engaged in creating your own impression of what it is. It's a creative process with room for your thought and your participation. That's why you shouldn't leave the class and drop the class and go into another room. Okay. Secondly, it gets students addicted to the thrill of discovery. This is really, really important. Most students, I know a lot of them, they see something they don't understand and it makes them afraid. It makes them not want to try. And what this POGL method does is it gives them a way to get into understanding something. And once they gain some confidence, they learn that something you don't understand is just a dissonant prelude to the resolution, to the aha moment. Oh, I get it. And once you get that aha moment, you literally get addicted to figuring things out. There's a dopamine squirt in your brain, all right? Literally addicted to this feeling of aha. So there's a dopamine, and then you begin to relish things you don't understand. Oh, there's something I don't understand. I want to learn more about it. That's what we want our students. That's the attitude we want our students to have. So, and finally, it satisfies what's called Rogers' 5 criteria for a readily diffusible innovation, which many of you are diffusing innovation, so I thought I'd throw this up here because you might be interested. But relative advantage, compatibility, lack of complexity, trialability, and observability. So if you want to look that up, Rogers wrote a book on how to diffuse innovations. Okay, it's very widely read in the marketing world. Okay, so these are some things students say. Discovering concepts made them their classes. I'm back. Okay, I fall asleep in all my other classes. In this course, I really learned how to learn. I never thought I would like chemistry. And finally, from a faculty member who's unfamiliar with this method, if the students are enjoying it, the course must lack rigor. In other words, if students enjoy my class, I must have watered it down. Well, let's see. Here's some data. So this is actually representative of lots of different data in different situations, but this is the largest sample to date. 750 students, a huge number relative to this type of work, we're taking at a top-tier research university. We're in Organic Chemistry 1, which follows into Organic Chemistry 2. And the students in Organic Chemistry 1, half of them were in a lecture section taught with a very excellent lecturer, and half of them were in a POGL section using the method that you previewed earlier. And all of, well, no, most. Nothing. How about? No? All right, fantastic. I'll use both. Okay, so get to work on that activity. Okay, so you're going to change the batteries. Okay, all right. And the batteries on that light need to be changed too. Okay, so all of these students, or most of them, went into a second section taught by lecture with a totally different professor. He didn't know who was from the POGL section, who was from the lecture section, and this professor in this section assigned grades based on how well students did in his course. Well, the students who had lecture for Organic 1 and lecture for Organic 2, their average course grade out of 4 was 2.5. That's about average. The students who had POGL for Organic 1 and lecture for Organic 2 in the lecture course got 3.0 out of. So this is half a grade level. This is a huge, relatively speaking, a very large difference for those of you who like statistics. An effect size of 52% is quite large. It's the ratio of, you can talk to me afterwards. So what we're trying to do is create a future in which classrooms are student active, cooperative, and discovery-based, where students learn content and these key scientific reasoning skills, not just skills in the way you normally think of it, but what I was talking about, the aha moment, the ability to look at a problem they don't understand and relish that moment, knowing that the resolution is coming. This is an opportunity for me to get a dopamine squirt. This is something hard, and I seek out hard things. I'm a scientist. That's what students should think. We want science to be widely viewed as a creative and fun art. And finally, diversity and innovation in science would increase dramatically if this were to happen, and the general scientific literacy increases. Voting trends would change. Many very interesting things would happen if we could get everybody in this room to learn organic chemistry. I'm serious. Or calculus or anything. All right, that's all I have to say. Thank you very much.